video, I'm going to be talking about two theorems of algebra. The first one is called the fundamental theorem of algebra. This says that every non-constant, so in that case it means it has to be linear, quadratic, or some other higher degree, single variable, it only must be defined in terms of x, polynomial function. So let me just say that again. Every non-constant, single variable, polynomial function. So what we've been working with this chapter, with complex coefficients. So basically any number has at least one complex root. Now a corollary to that is that every nth degree polynomial with complex coefficients has exactly n roots. Well, what does that mean? If I just wrote down a polynomial equation right now, let's say 3x cubed plus 4x minus 5 equals 0, I know that this must have 3 roots. This is a third degree, right? Its highest exponent is 3. It's cubic. It must have exactly 3 roots. No more, no less. So it's a pretty simple idea, and a lot of us have already been using this idea. So I'm going to use that in conjunction with this next, the rational root theorem. So given this equation, this polynomial equation, the rational roots of it must be of the form p over q, where p is a factor of the constant term and q is a factor of the leading coefficient. So here's a nice example. Notice we have a polynomial equation up here. It's equal to 0. So I'm just going to write one out. So 3x to the 4th minus 5x cubed plus 2x plus 1 equals 0. So 3 would be our a of n in this case, our leading coefficient. 1 would be our constant term. If this has rational roots, not every polynomial equation has them, but if it does, they must be of this form. P is a factor of the constant. Okay, well, what are the factors of this constant? 1 and negative 1. Okay, what are the factors of 3? 1, negative 1, 3, and negative 3. So what are the possible combinations for this fraction p over q? P are the factors over here. So we could have positive 1 over positive 1. We could have negative 1 over positive 1. We could have 1 over 3 or negative 1 over 3. I think that covers it. So there are 4 possible rational roots to this equation. That doesn't mean that they definitely are, but if they exist, they have to be of this form. Let's do an actual example. Here's a quadratic. Now notice, if I was going to find the roots of a quadratic, I could try factoring it, I could try graphing it, or I could use the quadratic formula. I'm just going to quickly factor this. This is, let's see, 2x and x, and this would be a 3 and a 1. I think this is 2x plus 3 and x minus 1. Does that look good? Looks good. So look at how easy it was to find these roots. You know, that theorem that we just introduced, that rational root theorem, well, it doesn't really help me figure out the solutions. I already knew them, right? So here I'd get that x is negative 3 halves, and here x is, x minus 1 equals 0, so x equals 1. Great, so I know the solutions. Notice that the factors of negative 3 are positive and negative 1, and positive and negative 3. The factors of 2 are positive 1, negative 1, positive 2, and negative 2. Are these answers of this form? Sure, because negative 3/2 is using the negative 3 over the positive 2. 1 is using the positive 1 over the positive 1, or I guess you could say it's using the negative 1 over the negative 1. So if I wanted to first come up with the possible roots that this gives me, I could then test out and see which of those are actual roots. In this situation, that wouldn't really be helpful. So let's do one where it might be. So here's our second example. We have a quartic. Notice we don't have a quartic formula. I can't look at this and know how to factor it right away. Maybe it is factorable. I don't really see it. It probably will be, if it was, it probably would be really annoying to do it. I could graph it, right? And if I graphed it, I actually would find roots. You can try that. Try finding that. So that would be helpful, right? But I'm going to show you what you would do if you didn't have a graphing calculator to find those roots. Okay, so the first thing. What are the possible rational roots? Let's start there. Well, we need our factors of 10. So our factors of 10, plus or minus 1, plus or minus 2, plus or minus 5, plus or minus 10. Okay, so we got all of those. Now let's look at our leading coefficient, the factors of 3. That would be plus or minus 1, plus or minus 3. Think about how many combinations you're staring at right now. We could write them all out. We'd have 1, negative 1, 2, negative 2, 5, negative 5, 10, negative 10. But then we would also have all of those values divided by 3. So we would have 1/3, negative 1/3, 2/3, negative 2/3, 5/3, negative 5/3, 10/3, and negative 10/3. Okay, so lots of possible rational roots. We could try until we found one that works. I'm going to start with 1 and negative 1 and see how that goes. Here we go. If I want to see if 1 is this a rational root, that would mean that when I perform synthetic division using 1 on this polynomial, what I really mean by that is that I'm trying to divide this polynomial by x minus 1. I can know if it's a factor if I get a remainder of 0. So let's try that. So if I perform my synthetic division, so 3 times 1 is 3. Add those together is negative 2. Multiply, I get negative 2. It's negative 19. Multiply, I get negative 19. Add together, I get 6. Multiply, 6, and 16. Okay, so we know that the remainder is not 0, which means that x minus 1 is not a factor, which means that 1 is not a root. Okay, so 1's off our list. Let's try negative 1. Here we go. Doing my synthetic division. Nope, not working. Negative 1 is also not a root. Let's try 2. Okay, again, performing my synthetic division. And it looks like my remainder is 0, which means that x minus 2 is a factor, and 2 is a rational root of this equation. So if 2 is a rational root, we now know a factor of this quartic. So let's begin to factor this quartic. We know x minus 2 is one of its factors, but from the synthetic division we also know that another factor is 3x cubed plus x squared minus 15x minus 5. So now we're only dealing with a linear and a cubic. Now let's take a look at this cubic. I hope that you realize that this cubic is actually factorable by grouping. So let's take this. I'm going to split it up into, I see two groups here that I like. I like this one and this one. All right. So the GCF of 3x cubed plus x squared is really x squared. That leaves behind a 3x plus 1. And then the GCF of my other group over here is really negative 5. So if I factor out a negative 5, that leaves behind a 3x plus 1 as well. Perfect. So now if I factor that, I factor out a 3x plus 1. I leave behind an x squared minus 5. Excellent. So I still have my factor x minus 2. I now have another linear factor, 3x plus 1. I have a quadratic factor, x squared minus 5. And that's equal to 0. So I can solve linear equations, right? So one of my solutions was 2. We already knew that one. Here, one of my solutions is going to come from this linear factor. So x equals negative 1/3. And then this quadratic, I think it's just easier to solve by getting x by itself. So if I square root both sides, x equals plus or minus root 5. So how do I know that I'm done? According to the fundamental theorem of algebra, this quartic equation had to have 4 solutions. So I used the rational root theorem to determine this root. That helped me factor into this cubic. This cubic happened to be factorable, which let me find these 3 other solutions.